Okay, let me share my slides. Can you all see my slides?
Yes.
Okay, great. Okay, so in the last two classes, I was talking about the physical layer and the data link layer. So the physical layer transfers bits by converting it into pulses or waveforms and transmits them over a link, right? Wired link or wireless link. That's what the physical layer does. And the data link layer strings bits together and creates frames because bits by themselves don't have any meaning. And you put together bits to create meaning out of it. And the data link layer is responsible for transferring these strings of bits or frames, as they are called, from one node to another node over a link, right? So that's what those two do. Now, we already saw that not every two nodes can be directly connected. So sometimes you have to go through intermediate nodes through intermediate switches, right? So how does a packet or a string of bits get from a host or a computer to another computer through intermediate nodes, through intermediate switches? Okay, so that's where the network layer comes in. So the network layer is responsible for the transfer of packets, which is just another term for a bunch of bits from a host. That means an end device like a computer or a smartphone or whatever device is connected to the internet to another host across multiple nodes and links. So this is generally considered the most complex layer of networking. Okay, because it requires the coordinated actions of multiple geographically distributed network elements, switches and routers, because it's not just one node that's making decisions. You have to coordinate with various other nodes to ensure that the packets are uh, transmitted from a host to another host, right? And must be able to deal with very large scales because the number of users and the number of network devices and the number of end devices is going to be very large in the internet. There are billions of users, right? Now, by one measure, there are 50 billion devices. There are only 7 billion people in the world, but there are 50 billion devices that are connected to the internet. Okay. So, some major challenges that the network layer has to solve are addressing. That is, how to identify an, a host or an end device. Okay. That's addressing. And second is routing. That is, what path should be used to get the information there. Okay. So here is what a typical campus network looks like. Campus is an organization such as CEG or a company or something like that, right? So you have many departments and you have some switches here. And these are computers that are connected that are networked through these switches. And here is a departmental server. So there are many such departments. And then the campus has a backbone network. So there are some switches in the backbone network, and there are these R, which are routers. Okay. Routers are basically connecting two different networks, as you can see here. A switch is something that is within a network. A router is connecting two different networks. And then the organization might have some servers. So if you need access to a database, then you would get that from the server. And this special router here is a gateway. This is a router that is connected to the external internet. So this is what a campus network looks like, and you're connected to the internet through an ISP, through an internet service provider, right? So here, this is a local area network. So, I talked about this last time. There are some special kinds of networks called local area networks, which use somewhat different kind of technologies than the technologies that are used in the backbone network. So the packets that are going from one computer to another computer here, they do not appear in the backbone network. They are completely routed locally. So only the packets that outgoing packets leave the LAN, leave the local area network through this router. Okay. And we already saw this high-speed campus backbone network connects department routers, and servers have redundant connectivity to the backbone. That means there are multiple servers. You see, there is multiple connections here. So if one of them fails, one of the links or one of the switches fails, you still have connectivity to the servers through other links and switches. Okay, that's important because just a failure of a single link or node should not disconnect your entire network. And this is the gateway, as I said. Okay. Now, how does the nationwide or network? What does it look like? So you're connected to the internet service provider. What's in the internet service provider? So we know that there are multiple internet service providers, right? So for example, here's a service provider A, service provider B, and service provider C. But these service providers have to talk to each other, because when you send an email, you can't say, what service provider are you on? If you're a different service provider, I will not be able to email you. That's not acceptable, right? So you don't care what service provider the other party is using, the recipient of your email is using, you still need to be able to email that person. So therefore, these networks, the networks corresponding to these different service providers, have to be connected to each other. Okay. And that is done through these network access points. There are some special points called as network access points where multiple service provider networks come together and connect to each other. Okay. Besides these common network access points, you can also have a two-way, meaning just two-party connectivity. So, for example, here service provider B and service provider C are connected through this link right here, which is called as a private peering point. Okay. Okay, so this is how the network is connected. So one of the important tasks of the network layer is the task of routing. That is, suppose you have a packet, and suppose you have decided how to identify the end nodes. I'm actually going to talk about this a little bit later, but suppose you have a way of identifying where you want to send this packet. Okay. Now the question is, how do you send the packet to that node? How do you find the path through the network? Because there are many links many links in the network, many nodes, and there are many paths. There are many ways. So how do you get the packet to the destination? Okay. The problem with this is that the network is completely decentralized, right? So you're not making decision. You're not sending all the information to some special controller node, and that controller node is making your decisions. No, we don't have that, because we have billions of devices that are spread out all across the entire world, right? So how do these decisions get made without a central entity? Okay. So the key to this is basically you do this in a hierarchical manner. Okay. There are protocols which are known as interior gateway protocols and exterior gateway protocols. So the whole internet is divided into a number of domains. And interior gateway protocols, or IGPs, are used to route packets within a domain. And EGPs, or exterior gateway protocols, are used to determine routes across domains, that is, from one domain to another domain. Okay. The main challenge in this case is that the routes have to be consistent and produce stable flows. What does that mean? It means, suppose a packet needs to be routed from A to C, and A thinks that the best way to get to C is through node B. Okay, so A is going to send the packet to node B, okay, and B has to send it on to C, right? But suppose B thinks that the best way to send the packet to node C is through node A, then B is going to send the packet back to node A. Okay, so this is an inconsistent route, right? A thinks that the best way is through B, and B thinks that the best route to C is through A. So this is going to cause a ping-ponging effect, which means the packet is going to just go back and forth between A and B. Okay, this is not desirable, right? So how to get out of such things? I mean, that's basically the challenge in one of the challenges of routing. Okay, and also scalability, right? So how do you make sure that this process of routing is scalable? That is, as the number of devices grows, the thing doesn't break down. Okay. So one of the things that helps with this is the hierarchical structure of addresses, or IP addresses. IP stands for Internet Protocol, as you know. So the hierarchical structure of IP addresses is extremely important to keeping the size of the routing tables manageable. So I'll talk a little bit about what a routing table is in a few minutes. Okay. So let's look at the problem of routing now. So this is a network. So represent it as a graph with nodes and edges or links. Okay. And let's look at various paths from node 1 to node 6. Okay. So let's say there is a computer at node 1 and there's a computer at node 6, and you need to send some information, packets, from node 1 to node 6. We can see that there are many paths through the network. For example, there is this dotted purple path here at the top, 136, and there is this dashed red path, 1456, and there is 1256, right? So there are these three different paths. Now, which one is the best? So you want to send it along the best path. Just like when we drive in a car, we want to find out which is the shortest route, which is the least congested route, and we put it in the GPS, and the GPS is going to tell us, what the shortest route is, how much time it takes, and so on. Okay, so same concept exists in a network here. So which is the best path? And how do you define best? Do you mean minimum delay, takes the least amount of time, minimum number of hops, that is minimum number of intermediate nodes, or the maximum bandwidth, or perhaps minimum cost? Maybe you're paying some cost to access each of these links, and maybe you want to minimize the cost, or maximum reliability. Maybe each of these links have different levels of reliability, and you want to find the most reliable path. What is your desired metric? Okay, so this is up to the network operator. The network operator can define, or can decide, can determine what they want to optimize, and then find the best path to optimize that metric. Okay, so suppose we have the paths that have been determined, right? So here's the same network topology, as you can see here, 1, 2, 3, 4, 5, 6, 6 nodes. Now, each of the nodes, in the case of the internet, right, has a table that looks like this. Okay, the table contains, this is a simplified version of what actually happens in the internet, of course. In simple terms, the table contains two entries, destination, or two columns, I should say, destination and next node. What these two columns say is that if your destination node is 2, then send the packet to node 2. If the destination is 3, send the packet to node 3. So here is node 1. It's directly connected to node 2, 3, and 4. Okay, it is not directly connected to node 5 and 6. So for nodes 5 and 6, you have to go through intermediate nodes, right? So if the destination is 2, 3, or 4, then the next node is obviously 2, 3, or 4. That's the next node that you need to send the packet to. But the destination is 5, so 5 is here, and node 1 is not connected to node 5, right? So you have to send it to one of the adjacent nodes, one of the neighboring nodes, right? There are 3 nodes here, 2, 3, and 4. Okay, the table specifies what path the packet is going to follow. In this case, the table says the destination is 5, the next node is 2, which means we're going to follow this path, right? So there you go. So suppose a packet is going to be sent to node 5. The table says the next node is 2. Well, who filled up this table? That's the routing algorithm. Okay, we'll talk about this soon. But suppose the routes have been determined and these tables are populated, right? So it says if the packet is going to be sent to node 5, the table says send it to node 2. So the packet arrives at node 2. Node 2 is going to look at the packet, and it has the destination address of 5 inside the packet. And it says the next node A is 5. So that means deliver it directly to 5. So this is the path that the packet is going to follow. Okay. So that's how, So that's how the packets are forwarded from the source host to the destination host by following the entries in the routing table that is present at each of the nodes, right? Now the question is, who is coming up with these entries in the routing table? Okay, now there's a big network there. Okay, how do you find these entries? Which should be the next node for each destination? Okay, that's the job of the routing algorithm, right? So as we saw earlier, there are multiple paths, right, to go from one node to another node. Here we see here that this is one path, this is another path, this is another path. Which one should you follow to go from 1 to 5? Okay. So routing involves the selection of the path to be used to accomplish a given transfer, right? So the way it is done is, as I said, there are many possible metrics for the network operator to optimize. You can optimize the distance, you can optimize the cost, you optimize the reliability, etc. Okay, but all of it boils down to a particular way of doing things. For example, you want to minimize the distance, let us say. Okay, then you assign the distance of each link as a number to that link, and then you pose the problem of routing as a shortest path problem. Okay. So let me So this just shows that there are a number of possible metrics. I've already mentioned this. So let's take a look at this particular example right here. So this is again the same graph here, and let's call node 6 as Chennai, right? So we are sending information from other nodes, maybe this is Bangalore, Bombay, etc., to Chennai, right? So you see these numbers that are right next to us. These numbers correspond to distance, okay? If you want to minimize distance, these numbers correspond to distance. So the distance or the length of this path from node 1 to node 6, if you follow this path, the length of the path would be 2 plus 1, which is 3, okay? So this is node 1 to node 3 to node 6, the length of that path is 3. If you go 1, 2, 5, 6, then the length of the path is 3 plus 4 plus 2, which is 9. And N1, N4, N5, N6, this is 5 plus 3 plus 2. So the length of that path is 10. Okay. So clearly among these three paths, we see that this is the shortest path, N1, N3, N6, because it has got the lowest one, right? So if you can say what the length of the link is, then you can find the shortest path from this. But sometimes you might want to use a metric that is not static, that is not constant, but that is changing. Okay, the length of the link is not going to change. That's fixed, right? So if you have a link between two nodes, that the length of that link is not going to change. But if I say delay is the metric, okay, the delay can actually change with time. So if there is more congestion, the delay is going to be higher. If there is less congestion, the delay is going to be lower, just like in the roads, right? So sometimes roads are congested and therefore it takes longer time. Other times the roads are not congested, therefore it takes less time. So this is dynamic. The delay is dynamic, right? So if you change this length to delay, for example, then these numbers that are on the links are going to be changing dynamically with time, right? So there are protocols that these two nodes, neighboring nodes, exchange to figure out what the link is over the past, X amount of time. So what is the average delay over this link? So that can be dynamically measured, and the link cost is assigned to be equal to that delay. Then if you find the shortest paths, then what you're finding is the shortest delay path, right? The smallest delay path, where the length of these links is dynamically changing. We call it the link length or link cost, okay? Now, in this way, the way that I formulated it, there are these three paths, and you can calculate the length of each of these paths by summing up the cost of each of these links, the cost or length of each of these links, right? Now, this is a small network or a small graph. Now, in a real network where there are thousands of nodes, the number of paths can be very large, extremely large, hundreds of thousands and millions even, right? So in that case, how do you figure out? Do you have to actually go through all of the million paths and figure out which is the shortest path? That might take too much time, right? So fortunately, there are actually very efficient algorithms that allow one to find the shortest path from any node to a given destination, okay? And there are two major classes of protocols. The internet started by using these so-called distance vector protocols, but it's evolved into these protocols, which are called as link state protocols, which is what is used in today's internet. So the idea is this, okay? So every node like this, okay, this could be a router, for example, in the internet. So it monitors the state of its adjacent links, that is, the links that are connected to it, right? So namely these links, okay? And calculates the link state, for example, delay, right? So it measures the delay on each of these links, okay? So that's called as the link state information. Then that link state information is flooded. Flooded is another term for broadcast, okay? This link state information is broadcast to all the routers in the network, okay? So this information about these links is going to be sent to every node. So this one, every node, okay? So every node is going to do the same thing. Every node is monitoring the links that are connected to it, and it's going to send its link state to all of the nodes, okay? So this node, for example, is receiving link state information from here, from here, from here, from here, from here. So every node is going to send its link state information. Okay, that is, what is the link? What is the delay on that link? Okay, if delay is the chosen metric, right? So in this way, every node basically has the map of the entire network. It knows what nodes are there in the network and what are the delays or the costs of the links that are connected to that node. Okay. So you have the complete topology information. That is, you know all the information that you need. You know the entire map of the network, and you know all the delays and all the costs. Then you can run the shortest path algorithm, right? So the shortest path algorithm does not require you to actually find all of the paths and then calculate the costs of each of those paths explicitly. Like I said, there might be millions of paths in a big network. Okay. Fortunately, there is a well-known algorithm that allows you to compute the shortest path in a very efficient manner. Okay, so this algorithm is called as a Dijkstra shortest path algorithm, named after uh, the person who invented this algorithm, Dijkstra. The J is silent there, right? So Dijkstra shortest path algorithm. This is a well-known algorithm that has many applications, not just in the internet, but in many cases. You know, your GPS uses some kind of a Dijkstra shortest path algorithm as well for navigation. Okay. So that's how you find the shortest path. And once the shortest path is determined, then you put the information in the routing tables so that the packets can be forwarded in the desired shortest path. Okay. The other thing that I haven't talked about yet is how nodes are going to be identified in the internet, the addressing part. I'll talk about that soon. Okay. So the main protocol at the network layer is called IP, or Internet Protocol. And there are a couple of other associated protocols that are, you can think of them as helper protocols for IP. Okay. The actual protocols are not important for us, the ICMP and ARP and so on. Okay. So these are this is the network layer protocol. And below the network layer, recall that there are two layers, namely the data link layer and the physical layer, right? Now, the data link layer and the physical layer are typically combined and implemented in a network interface. What's this network interface? This is, for example, a Wi-Fi card or an Ethernet card that is plugged into your computer. Okay, that's what this network interface is. So it combines the data link layer and the physical layer into one piece of hardware. Okay, so when you send a packet to the network interface knows how to make a frame out of it, how to recover from errors, and how to convert the bits in the frame to whatever waveforms that you need to use to transmit over the medium that is used by this network interface. For example, Wi-Fi, it's a wireless interface, right? So it's a, you send it as radio waves. If it's Ethernet, which is a local area network standard, then you send it over a wired medium, okay? And there are some specific waveforms that are used for that medium. So the network interface is taking care of all of that job, okay? So for the IP layer, what it needs to do is simply create packets, make sure that the packets can go from the source to the destination host, okay? And the job of error recovery and converting the bits to waveforms, etc., that's taken care of by the network interface. So you don't need to worry about that, right? So if you write an internet application, you don't need to get down to the level of detail of what waveform should I use for this particular bit, because that's already implemented in the network interface. So you just call the network interface and say, hey, here's the packet, get it to the other node, okay? And the network interface is going to do that, okay? Okay, so IP is the network layer protocol, and above the network layer is the transport layer, right? And I'll briefly mention what the transport layer is later, but there are two main protocols, TCP and UDP, at the transport layer, and sitting on top of this are various applications. You all know what HTTP is, and SMTP stands for Simple Mail Transfer Protocol. This is a protocol that's the heart of all email programs, right? Now, the email programs that you have, Gmail and Outlook, etc., they're basically at its heart, it's using the SMTP protocol. in the way they display the email is all different in the different applications, right? Outlook may organize messages in one way, threads and conversations in one way, Gmail does it in a different way, but that's about it. At the heart of it, to actually send the information from one node to another node, it's going to use the SMTP protocol, okay? And this is domain name systems, another protocol that's used in the internet, and it uses UDP, a transport layer protocol, okay? So the success of the internet is mainly because this internet protocol is able to work with different kinds of network interfaces. So if a new, technology comes up, optical fiber or satellite or whatever it is, you just need to find a network interface that adapts to that physical medium, okay? And you can use IP along with that, okay? Same thing at the top here. You could have, so there are a couple of basic types of services, transport layer services, and you can build, you can use these services to build different kinds of applications, okay? So let me say a few words about addressing now, okay? So addressing is the way of identifying a host on the internet, or anything that is connected to the internet, right? So you may think, well, why is this a big deal? I mean, why don't we just call and give it a number and that's it, Actually, it is a big deal because one of the main requirements in the internet is that it has to be scalable, right? That means the number of such hosts could be in the billions, right? So that means the address has to have a certain kind of structure, okay? We have that kind of structure in postal addresses and telephone numbers, okay? And there is a very good reason for that, because that also needs to be scalable, right? So if I want to mail a letter to somebody in Chennai, then I would write, okay, Mr. X, some Ranganathan Street, T Nagar, Chennai, and a pin code, right? That's how I write it. And then India, if it's coming from abroad, right? How does that help the postal service to deliver the network? First of all, when they say India, okay, if I mail it from the US, they know exactly where it's going. It has to be sent to India. They're not going to bother about is it going to Chennai or wherever at this point. They simply send it to a central processing point in India, and then it's going to be sent to Chennai, and then it's going to be sent to T Nagar, and then the particular house, right? So that's how the letter is going to be routed, right? People are not going to start thinking about Ranganathan Street when I mail the letter in the US. The post office here is not going to worry about Ranganathan Street. They say, okay, this is going to India. That's where I need to send it, right? That hierarchy helps in routing. They don't need to look at the rest of the address. They just need to look at the country name here to send the letter, right? So it simplifies things, okay? You only need to process a certain part of the address. Okay, same idea is used in telephone numbers as well. You have the country code, area, city code, etc. Right? So the internet addresses also follows the same pattern. Okay. Now every device that's connected to the network has a unique ID. Okay. That ID is called as a MAC address, or a physical address, we call it sometimes. It's 48 bits long that uniquely identifies every piece of hardware that's attached, that's connected to the internet. Okay. But computers can move from one network to another network, right? So if I'm on a laptop or a smartphone, I'm connected to one network right now. But when I go to some other place, then I'm going to be connected to a different network. If I'm traveling, if I'm connected to the hotel network, then I'm going to I'm connected to a different network, right? Now, if I carry the same physical address everywhere, then that makes location of my device hard, right? Because I lose all of this hierarchy thing that, I won't have this hierarchy stuff because my address is fixed, right? When you move a house, your address is going to change. You cannot keep the same address when you move a house, right? If you move from Chennai to Bombay, you're going to get a different address, right? So similarly, we need to have a different address when we move from one network to another network. That's where the IP address comes in. So you have a physical address that identifies your device, but there is also a logical address or the internet address, IP address, that basically identifies, that has this hierarchical structure that identifies where you're located in a sense, right? Okay. So when normally when you send an email, this is my email address, suresh@gwu.edu, you're going to use this one, right? Now, computers, of course, do not use this. This needs to be converted to the address that can be used by the internet. Okay. So this is going to be resolved by the domain name system, okay, into an IP address. And the dominant form of IP, which is IP version 4, okay, or it has been the dominant for a long time, looks like this. And you're all probably familiar with this kind of notation here, right? 128.100.10.13. Okay. What does this mean? Each of these is basically a number between 0 and 255. It's a decimal number between 0 and 255, and that stands for an 8-bit number. Okay, so we know with 8 bits, we can represent a combination, any number from 0 to 255. If all 8 bits are 0, that's 0. If all 8 bits are 1, that is 255, or the decimal, the binary representation of 255 is 8 ones, right? So that's what each of these numbers is. 128 means 1 followed by 7 zeros. Okay. 10 is 1010 or 0000 8 bits, right? So byte is also called as octet. Okay. So this is actually a 32-bit address. We write it in this form because it's easier for us to read it this way as opposed to 10000000, etc. Right? So this is a convenient way of writing a 32-bit address. Now, the important part here is that this address is hierarchical, not just because there are dots here, but this is how I mean. So this address is actually divided into two parts called the network ID and the host ID. Okay. The network ID is unique, and that corresponds to what network you're attached to. And that is what facilitates routing. So when a router looks at a packet and say, where is this packet going to? It's going to look at the network ID field of the packet and determine, okay, this host is on this network. So this is where I need to send this packet. Okay. So let me show you a simple example here. So suppose there are two networks here. Okay. For example, this is one department network or one organization's network. This is another organization's network. But they're both connected to the internet, so therefore they have to be connected by a router at some point, which is here. Okay. So R stands for router, H stands for host. Host is the computer, right? So this network has the address 128.135.0.0. This is the host part, host ID part. This is the network ID part. And this network has the address 128.40.0.0. So notice that this network has a different address compared to this network. And this network has 3 hosts attached to it. All hosts must have the same network ID, as you can see here. They all belong to the same network. But the host ID is different, obviously, because they are different hosts. The host ID is unique to this network for these different hosts. So this host has a different ID than this host, than this host. Similarly, this network has 2 hosts, and both hosts have the same network ID right here and different host IDs. Okay. These two networks are connected by a router. So this router is really, it has 2 network interfaces. One interface to this network and one interface to this network. And therefore, it has 2 different IP addresses, one for each interface. So this interface has this address. Notice again that this is the same network address as this network, and this is the host ID field. And this interface has this IP address. Okay. And the network ID field is the same as this network address. Okay. And there are a couple of special address fields that are for specific things. For example, the all zeros in the address field refers to the particular network that it's attached to. And if it's all ones in the host ID, that means the packet is supposed to be broadcast to all the hosts as opposed to sent to a specific host, and so on. Okay. So this is the general idea of addressing. Okay. There are a lot of details here that I'm not going to go into now, but there are different address types to cater to the needs of different sizes of networks. Some networks are small, some networks are large. Now, I'm not talking about the internet here. I'm talking about various organization networks, right? So if it's a small business, then there might be just 100 computers in that network. But it's a very large company, then they might have millions of computers in their network, right? So the addressing scheme allows for different kinds, different sizes of networks to be present and to be interconnected with each other. Okay. So as I said, the original widespread IP version is IP version 4. Okay. But in the mid-90s, it turned out that it was becoming apparent that we're going to run out of addresses, okay? Because we have 32 bits per address, okay? Now, if you have 32 bits, if you use it as a flat address space, then you know that you can address 2 to the 32 devices, right? All zeros to all ones. So that's 2 to the 32 different devices. 2 to the 32 is approximately, 4 billion, right? 4 billion, but we know that the number of devices is a lot more than that, okay? But because of the hierarchical structure, the actual number of addresses that can be used is a lot less than 4 billion, okay? So these addresses were running out. Furthermore, the routing tables, recall that every router has a table that says for every destination, what is the next hop, right? As the number of destinations increases, the number of entries in the routing table is going to increase. Okay, so that means you need to search through a very long table to figure out where the packet needs to be where the packet needs to be sent. Okay, so that started slowing down the search process. Okay, so there is a solution that that was developed to address this, and the solution is to increase the address field size from 32 bits to 128 bits and simplify many less used features. Okay, and this doesn't solve this slow table lookup problem, but the addresses were organized so that the addresses can be aggregated together, and so a router that is in the core of the internet does not have to look at the entire 128-bit address field, but only a small portion of the address field. Okay, so it simplifies the lookup process, the address lookup process. So this version is called as IPv6, and it's deployed in a number of networks already, but not everywhere in the world. Okay, so for some time we're going to have both IP version 4 and IP version 6 coexisting. Okay, so what do you do when you suppose the source is an IPv6 source and the destination is an IPv6 destination, which means it's on an IPv6 network, but the packet needs to go through an intermediate IPv4 network because not everybody has upgraded, right? This is just like when when Windows releases, when Microsoft releases a new version of Windows, usually it's backward compatible to the last few versions. But then at some point, Microsoft comes and says, okay, we're not going to support Windows 95 anymore, right? So some programs that were designed for Windows 95, when Windows 95 came out, for example, are not going to work, and you have to move on to other things, right? So similarly here, V6 is supposed to be backward compatible with V4, but it might stop this, at some point of time, this backward compatibility might stop being supported. Okay, but for now it needs to be supported because there are just 2 versions of IP. Okay, so the way it is done is, so this is an IPv4 network here, which means it doesn't understand the language of IPv6 because it's a different protocol. So the way it is done is there's a tunnel that is created from this end, which is an IPv6, to this end, which is also an IPv6, through the IPv4 network. Okay, so this tunnel basically makes the entire network path look like a direct link, like this. Okay, so I won't go into any more details than this, but this is how the 2 versions of IP can coexist with each other, and we don't run into any kind of problems. Okay, I won't go over this particular. Okay, maybe I will go to it. Okay, so the global internet, the internet that we all are familiar with, can be viewed as a collection of autonomous systems. So what is an autonomous system? Autonomous means, as you know, it's independent, right? Something that is an independent entity is called as autonomous. So an autonomous system is a set of routers or networks that are administered by a single organization. Okay. For example, CEG has a network. That's an autonomous system. Okay. So the administrators of the CEG network are responsible for how packets are going to be routed inside the network and so on. Okay. So there are three types of autonomous systems. Most autonomous systems are what are called as stub autonomous systems. Stub autonomous system has a single connection to the outside world. Okay. Stub autonomous systems, or they could be multi-homed. So single connection to the outside world, which means that you are connected to the outside world, to the external internet through maybe one gateway router. Okay, so that would be a stub autonomous system. A multi-homed autonomous system has multiple connections to the outside world. Okay, for example, maybe you don't want to rely on just one ISP. So for reliability purposes, maybe you want to be connected to two different ISPs. So if one service provider goes down, you're still connected to the internet through the other ISP. Okay. In certain critical cases, you might want to do that because you don't want to lose connectivity when something goes down with one provider's network, right? So you could either be a stub autonomous system or a multi-homed autonomous system, depending on what level of reliability you want. Okay. Then the third kind of autonomous system is called as a transit autonomous system. Transit autonomous system is connected to multiple other autonomous systems, and they can carry transit traffic as well as local traffic. Transit traffic means traffic that is coming from some other system and going to some other system. So it's passing through. Okay. So an example of a transit autonomous system are the ISPs. Okay? The job of the ISP is to carry traffic, internet traffic, on behalf of its customers. Okay, that's their job. They get paid to do that, right? So customers pay money to the ISP, saying, "Okay, here's some packets, or some email or whatever it is that I want you to transmit to this user in the other network." So the ISP will gladly do it because you're paying them to do that. Okay, so those autonomous systems are called as transit autonomous systems. Okay. So I already mentioned this earlier, but I won't go into more details here. So I talked about interior gateway protocol and exterior gateway protocol. Interior gateway protocol is a routing protocol that is used within an autonomous system like this. Okay, so this is an autonomous system. Three autonomous systems are shown here. A routing protocol that is within each of these is called as an interior gateway protocol. And here are some examples of interior gateway protocols. RIP OSPF, this is the most popular one, ISIS, and so on. Exterior gateway protocol is the routing protocol that is run between these gateways that connect two different autonomous systems, like here. Okay, so the protocol that is used there is called as BGP, or Border Gateway Protocol. Okay. So OSPF is the most common interior gateway protocol, and it's a very complex protocol. Won't look into the details, but the idea is it follows that link state method that I mentioned earlier. That is, every node broadcasts its adjacent link states to all of the other nodes in the network. Okay, so each router builds an identical link state database. So using these link state packets, every router is going to build a database and allows the router to build a shortest path tree with the router as the root. So ignore this part right here. It simply means that you can find the shortest paths from that router to all of the other routers. Okay, so that's the protocol, which is called an open shortest path first. Okay, now exterior gateway protocols. So this is the routing protocol between autonomous systems. Okay. Remember I said a shortest path routing is the smallest delay and the minimum cost, etc. All of those things can be done only within an autonomous system. But when you're going through multiple autonomous systems, you have no control over what kind of routing another autonomous system is going to use in its own network. Okay, so it's not possible to say I want to minimize the end-to-end delay from a user in this autonomous system 1 to a user in autonomous system 3. That's not possible because you're going through multiple other intermediate networks, and those networks follow their own rules about what is the best path. Okay, so that's not even a goal here. To find the optimal path is not even a goal here. Okay, so the routing here across autonomous systems, that is through intermediate autonomous systems, is really guided by arrangements. So AS2, which is like a network, makes arrangements with AS1 saying, okay, I'll carry traffic on your behalf. And maybe there's a reverse arrangement as well. Maybe you carry traffic on my behalf. That is, I'll send you traffic that could be sent to other autonomous systems, and I'll take traffic from you and connect and send that traffic to autonomous systems 3. So that could be an arrangement between AS1 and AS2. Okay, so it's these kind of pairwise arrangements between autonomous systems that are made sometimes to carry traffic. Okay, so these are called as peering arrangements. Okay. Okay, this is kind of what the internet looks like. This is another figure of what the internet looks like, right? So this is a tier 1 ISP, which means a large nationwide ISP, for example, right? So this is tier 1 ISP, and these are various autonomous systems. Tier 2 transit autonomous system. So it's kind of, they're all interconnected. Okay, so within an autonomous system, the traffic doesn't exit the autonomous system, so it doesn't have to go to these tier 1 and tier 2 ISPs. Okay. All right, I'm going to conclude by just saying a few words about transport layer protocols. Okay, there are 2 transport layer protocols. So the network layer, recall that it transfers packets from a host. You can think of a host as a computer to another computer. That's what a network layer does, right? Now, within the computer, I could be running multiple applications. I could have a web page open, I could have an email application, and I could be listening to, watching a YouTube video, right? Now, I might be receiving data from the network for each of these applications, right? I might be loading, I might be watching some, looking at news on one website. And at the same time, I might be watching a YouTube video on another one, right? So, but they're all coming to the same host. So the data for each of these applications is going to be coming to the same host. And they have to be divided. After it comes to the host, the information has to be sent to the appropriate application. Okay. How does that happen? Well, TCP or the transport layer protocol ensures that the data is delivered to the correct application. Okay. So that's one of the main roles of the transport layer protocol. Okay, UDP is a very simple transport layer protocol. It does not do it. It does what is called as best effort. Best effort means it will do the best it can, but it's not going to try to optimize the performance or recover from errors and things like that. Okay, it is simply going to do the job. It's going to deliver it to the right application. That's about it. It's not going to add any extra value to it. Okay, it's a very simple protocol, but surprisingly, it's used by lots of different applications. Particularly multimedia applications. It uses this UDP protocol because it's very simple. It's also fast, which means it does not introduce extra delays. Okay. TCP is the other dominant transport layer protocol. So that the TCP and IP, the combination is so common that you might have heard this TCP/IP phrase a lot, right? So this is a much more complex protocol. Implements error recovery and flow and congestion control. That it reacts to congestion within the network, adapts its transmission rates, and so on. So pretty complex protocol. There's been tons of research that is done in analyzing its performance and improving it and so on. So, I could spend a year talking about just TCP. Okay, that is a class that spans 2 semesters. But for our purposes, I'm just going to leave it here. There are many applications that use TCP, FTP, file transfer protocol, HTTP, which that's used by your browser. SMTP is the mail transfer protocol, Telnet. All of these things use TCP's service to do their job. Okay, so we are almost out of time. So thank you for your attention. And if you have any questions, please feel free to ask. I can stop sharing. So. Any questions?
Yeah.
I hear some noise, but that's it. I'm not able to make out what you're asking. Karthik?
Yeah, can you hear me?
Yeah, now it's a little bit better. It's still broken, the audio.
If the students have other questions, it's all right. But I also wanted to hear a few words about maybe your focus areas for research.
Oh, yeah, that's a good question. I'll talk about that a little bit. Unfortunately, I couldn't have this class last week or a couple of days back. This is what I wanted to cover. Then today's lecture, I wanted to do something about what I do. So what my area of specialty is, broadly it's networking, but more specifically, it's fiber optic networks. That's what I work on. What is fiber optic networks and why is it special? What is so different about fiber optic networks? So first of all, what are fiber optic networks? Fiber optic networks are networks whose links are optical fibers. Okay, optical fibers means you use light, okay, to transmit information from one node to another node. Okay, this light is usually transmitted by a laser. Okay, so the laser has to be modulated with the information, and that information has to be transmitted from one node to another node. Okay, so what is the advantage of fiber optic transmission? Turns out that this is the best network link that you can hope for because it provides huge bandwidth. Okay, a single fiber actually provides a data rate of multiple terabits per second. Tera is 1000 giga, right? So you all know gigabits per second. Tera is 1000 giga. So a single optical fiber allows for transmission rates up to terabits per second, okay? Which is actually too high for any known man-made source. No source can generate data that fast. Okay, so what do? We have to actually combine the data from multiple sources and transmit them over a single fiber. Okay, by the way, fibers are basically the backbone of the internet. Okay, they're everywhere. They are the ones that are carrying traffic from one continent to another continent. Now, if you make a phone call, from India to the US or Europe, your phone call is going to be carried through an optical fiber at some point. Okay, there are lots of cables, and as we speak, there are cables that are being laid by ships under the ocean. So these are going to be buried under the ocean floor. Okay, and it's not just telecom companies that are laying fiber cables now. It's also the big Googles and Facebooks. Okay, because they process so much traffic that they find it more economical to have their own network. Did not used to be the case earlier, but now this is what they do. They have their own network, so they are laying fiber cables themselves. Okay, so fiber optic transmission is one thing. So that is, you use light to transmit data from one node to another node. Okay, it turns out that the full benefit of this optical transmission can be realized when you also are able to switch the data in its optical form. Okay, so previously what used to be done was you had the digital data, the electrical pulses and so on. So you converted that to light, you transmit that over optical fiber, and then when these optical pulses arrived at the other node, they would have to be converted back to electrical signals, and then you would do header lookup and all of that stuff to send the information to the next router and so on. Okay, that's how it used to be done. But it turns out that this process of converting from optical to electrical at every node is tremendously slow. Okay, therefore, to realize the full benefit of optical transmission, you also have to have optical switching. Okay, and that's where it's very exciting. So optical switches don't slow the signals down. But the problem is these optical switches are not as powerful. You cannot do, you cannot read various bits in the header and things like that. That's not possible in optical switching at this point. So it does a different kind of switching. Okay, so that imposes certain constraints in how the network can be constructed. Okay, so my research basically looks into how to get the most out of the technology that we currently have in optical switching and networking.
Thank you so much, Suresh. If the students have other questions, it's great, but otherwise I do have a follow-on.
Sure.
So you mentioned, optical switching. Although we hear in the semiconductor side of the world, when we hear about, on silicon lasers and so on, right? On silicon
yes.
optical transmission. So
right.
Are those relevant, or are they related to this optical switching? Are they applicable there? We only hear about them in data center networks and so on.
Right, they are definitely relevant, but they're having a laser on top of silicon is more relevant in the case of data centers. Here, for long distance, the switches have to be, they are more like what shall I say? The reconfiguration speed is not. You don't have this to be very high. Okay, so. You don't have to have the silicon thing in a large optical switch. These large optical switches are MEMS based usually, right? So which use mirrors to orient the light in different directions.
I see. Got it. Thank you.
I have a little different question. Just in terms of the future, we see the Starlink services coming in. Is it going to take out like the physical, connections, or is that going to be just one more mode? How do you see like that coming into picture?
Okay, what is Starlink? I'm not familiar with that.
It's like using satellites in low orbit.
Oh, yes. Okay. Yeah. Okay. So yeah, I would say satellite is an additional way of connecting things. So it's especially useful for rural areas or remote areas where it's hard to provide wired connectivity, right? So that's where satellites are useful, but it's not going to replace fiber optic transmission. I mean, for the foreseeable future, long distance communication is going to be dominated by fiber optics.
It's more
because nothing, because nothing comes close to the bandwidth that fiber provides. The downside, of course, is that it is expensive to lay fiber. So unless there is a very solid business case, which exists for long haul communications, you're not going to install fiber, right?
Yeah.
Any questions from students? The students are very quiet.
We should have extra points for whoever asking the question. I'm just kidding. There are no extra points, but just letting know.
Right. Okay. Well, it's been a pleasure, and I think the next lecture is going to be by Professor Bhuvana Krishnaswamy. She's going to talk about a specific wireless technology in her 2 sessions.
Thank you so much, Suresh.
Okay. Thank you all.
Happy to. I'll stop recording. Thank you.
Okay. Bye.